Yeah, then one task for today that we can have a look at in our exercise booklet is if I go to the exercise material and open it up. So the topics for today are this 18 and 19, and here's our nice exercise booklet. And as we've maybe discussed before a bit, it's about electrical power and the maximum power transfer theorem. And we have this nice circuit here. And the thing is that, yeah, there is already a very nice solution from the last semester, so that I've opened up here with another co-worker of us, not Anna, but Francesco. And there you find a very nice solution of these tasks by hand. So I don't see a big value in just repeating this. You can have a look at this recording. What I would like to do is to show you some software, if you like. And the software that I would like to use for this purpose is called LTspice. So I will try to find it and locate it on my computer. And this LTspice software will also be available in the computer lab where you do the exam and where you do the assessment. And I'm using I think an older version. The newer version looks slightly different, but has the very same functionality, just as that the buttons look a bit different. And every time it's telling me that I should update now. I've not updated since 2 years or so. So anyhow, if you open up the software, and it's called LTspice, it looks like this. So this is some circuit simulator, and there's a question.
Is that available for us to use at home?
Yeah, and you can download it. So I will maybe quickly go to my browser and open up this website. So this LTspice is named after a company, Linear Technology. And Linear Technology was 5 years ago or so bought by, or even maybe 10 years ago, bought by another company called Analog Devices. Still, this simulation program was so well known and so common that they did not change the name to DSpice or something else. So the LT still stands for Linear Technology. And SPICE is some abbreviation for simulation program with integrated circuit emphasis. Something like this. Yeah, like laser is, does anyone know what laser means? Light amplification by stimulated emission of radiation. And so, yeah, and the SPICE is a nice simulation program. And as you can see, it's fast, it's free, it's, I would not say unlimited, but it's, it has very few limits, and you can use it and download it free of charge. And you can even use it as a company. So many companies are using it. And this easy EDA that we discussed before in the background is also using LTspice as a solver. Just that they have a web interface so that you can use it from a browser. The disadvantage here is, let's say, that you need to download it and install it on your computer. It will run under Windows and Mac OS, and I think for Linux you need to have some emulator. But in general, it's working quite nice. So this is when you open it up, and now maybe I will try to arrange my screens in a way that I put the exercise booklet on this side and this on the other side. And then I maybe need to change here for the hand tool and maybe make this a bit smaller so that everything fits on the screen. Okay, so if we, before we are starting a simulation, let's think about, at least think about the solution of this. How would you solve this task, even if we not do it? So we have the circuit, we know all the values of these 4 resistors, we know the value of this voltage source. And we want to know what is the resistor with the highest power loss and how large is this power loss. So what would you do to solve this by hand, let's say? . Any ideas?
Use voltage divider.
We could try to use some kind of voltage divider. So we could calculate, or maybe I can try to use my drawing tablet here if this connects with my computer. So we could calculate, but this is the same as my mouse. We could calculate the equivalent resistance of these three here. So these two are in series and this R2 is in parallel. And then we could have a first voltage divider calculating the voltage drop at this position here. Yeah, also maybe maybe I will do a screenshot and not really do it by hand, but at least to give you the idea. And so we could calculate the equivalent resistance of this one here that we could call R234, and this would be R2 in parallel to the series circuit of R3 and R4. So we know the equivalent resistance of this. And then how would we set up a voltage divider?
R1 over R1 plus R234.
So we could say, okay, this voltage here, V1, would be the same as our source voltage multiplied with R1, the partial resistance divided by the total resistance of the circuit, and this would be R1 plus R234. Okay, then we would get this voltage. Then if we know this voltage, how do we get the power? Okay, power in the first resistor would be V1 squared over R. Okay. So then next question is, how do we get the other powers or voltages in the other resistors? We can use a second voltage divider, for example. So maybe to calculate this voltage here, V2. So how would we get V2? Say again?
The voltage across R2 is the same voltage across R2.
Yeah, and of course this voltage here would be the same as this voltage. This is also V2. Yeah, but does this really help us to, or I could also call this maybe V34. Okay. Unfortunately, I also don't know this voltage. So what else are we going to do? So let's think about this equation here. So we have a total voltage, and from this total voltage and the partial resistance divided by the total resistance, we can get this partial voltage. This is another partial voltage that depends on this total voltage. So how can we get this partial voltage? It's what's left. Yeah. Okay, we could say it's V source minus V1. This is not really a voltage divider, it's just the Kirchhoff's mesh equation. But this should work, and the other way, writing it down with some voltage divider would be we take this resistance R34, the partial resistance divided by, once again, the total resistance, 234. And then we get this voltage. And okay, and then we could do the same equation also for P2 until P4 equals V4 squared divided by R4. And okay, and then the question is, how do we get V3 and how do we get V4? We know V2.
And we know V34.
Yeah.
So V34 multiplied by R3 over R3 plus R4.
Okay, exactly. So this is once again the total voltage across this voltage divider. So this is a very simple voltage divider, just R3 as the partial resistance divided by the total resistance, and here the same V34 multiplied with the partial resistance divided by the total resistance. Okay, so then let's go to Octave and try to put in all the equations there, because this is, let's say, my favorite calculating tool. This is also something that you will have available in the exam. So I will clear all the stuff that is there before, and we need to insert all the values. So the source voltage is 100 volts, R1 is 30, R2 is 210, R3 is another 30, and R4 is 75. And then we can insert these the voltage divider here and say, okay, V1 is V source multiplied. Okay, and we need to have this the equivalent resistance first. So how at the end do we calculate this parallel circuit? If I have something, let's use a different color. If I have something like R1 in parallel to R2, how can I calculate this?
R1, R2, R1.
Yeah, the product of the two divided by the sum, right? Okay, so then let's write a quick function for this. So we can say parallel is a function that depends on R1 and R2, and if we want to calculate this, we need to have R1 multiplied with R2 divided by R1 plus R2. So now we have a nice function, and with this function we can say R234 is is the parallel circuit of R2 and R3 plus R4, right? This is what is written there. At this position, and so we get some value. And with this, then we can calculate V1. This is the source voltage multiplied with this voltage divider, R1 divided by R1 plus this R234. Okay, we get 30 volts. Then we could calculate V2 by saying this is V source minus V1, and we should get 70, and we get 70. We can also calculate V2 by the second voltage divider, V source multiplied with the partial voltage divided by the total voltage, partial resistance, and total resistance. Okay, and then there's some syntax error because I don't know, I pushed the wrong button on the keyboard. And with this formula, we also get 70, which is nice. Okay, and now we can calculate the remaining voltages. So V3 is V2, which is the same as V34 multiplied with R3 divided by R3 plus R4. And we get 20 volts, and then we could say, okay, V4, that should be once again the difference between V2 and V3. So from 70 and 20 we get 50. And we could also do it this way around to say V4 partial resistance divided by total resistance. And then we should also get 50. So now we have the 4 voltages. And from the 4 voltages, I could calculate the 4 powers. So P1 is V1 squared divided by R1, and so on. Before I calculate all these, is there some mistake? Is there a question?
Interesting one. He was wondering if we could just calculate equivalent resistance for the whole circuit, know the current,
Yeah, we could also do this. We can try to do this in a second. So there are many ways to solve this. So before I calculate the power value, one thing is that I would like you to think about. So if you have this circuit, and if we are thinking back about the task, what is the resistor with the highest power loss?
I wanted to ask something else.
Yeah, sure.
Wouldn't most power loss would be at the resistor with the highest resistance?
That's the thing that I would like you to think about. So if we have, let me take a different color once again, maybe gray. So if we would have something like this, so we have a voltage source and we have two resistors in series. And okay, this creates some voltage, and then we have a current, and we have some resistance R1 and R2. So power, electrical power is,
I squared R.
yeah, or current times voltage, I squared times R, or V squared divided by the resistance. But here we could say, okay, power is voltage times current, or current times voltage. If we have the same current through both resistors, our voltage divider rules tells us the higher resistor will get more voltage, and if the higher resistor will get more voltage, then it will also get more power. So exactly what you said, the largest resistor in the series circuit should get the highest power. So now think about, okay, now we have a parallel circuit of two resistors. And still we have a voltage source, and so now we have the same voltage here and the same voltage there, and once again we have two different resistors, R1 and R2. So, but now we have different currents through these resistors. So we have a current I1 and we have a current I2. So now what happens?
More resistance, less power.
Yeah, the more resistance, the smaller the current, and the voltage is the same. So smaller current means less power. So here, more resistance means more power, less resistance means less power. So now take a look at the circuit. And the answer is, no one knows. Difficult to say. Yeah? Usually we would say, okay, this resistor gets all the current, but it does not get all the voltage. And it's quite small. Yeah? This is just 30 ohms, so yeah, probably not. This one gets lots of voltage, but it's pretty high, so it only gets quite a few current, so maybe also not. Yeah? And these two resistors, they get a lot of current and in total also a lot of voltage, and the second resistor is much higher than the first one, so this gets the same current as this one, but much more voltage than this one, and still quite a lot of voltage. So yeah, without calculating, no one can say, but this resistor R4 seems to be a quite good candidate to get lots of power, because it's not too high to have a few current, and not too low to not have enough voltage. Yeah, it has the right amount of resistance to get a fair amount of current and voltage at the same time. Okay, so coming back to Octave, now we can calculate, and the power in the first resistor is 30 watts. The power in the second resistor is just 23 watts. The power in the third resistor is just 13 watts, and the power in the fourth resistor, and make some applause for the fourth resistor, because this is the one with the highest power, 33.3 watts. Okay, which questions do you have so far? let's do it with the current, right? So we could calculate the total resistance of the circuit, and this should be R1 plus R2, 3, 4, right? Okay, so this is the total resistance, it's 100 ohm. And so now we could calculate the current through the first resistor, right? The current through this one here by saying this should be also the same current that goes through the source. So it's the source voltage divided by the total resistance. Do you agree? Okay. So we get some current of 1 ampere. And so now if we once again calculate the voltage across the first resistor here, this voltage is also the resistance times this current. Do you remember the value that we had before? I wouldn't either, but here it's written before we had 30 volts for the first voltage. So if we try it with this equation, we once again get 30 volts. And so now you could also do it the same way and say, okay, now we know this voltage. Now as a next step, we could calculate this voltage using this equation, the mesh equation. And if we know this voltage from Ohm's law, we could calculate this current. And if we know this current and this current, we could calculate the other current. And if we know this current, we could calculate this voltage and this voltage. And then we also know all voltages or currents. Okay. So now that we have some results here already in Octave, how could we do a quick sanity check that this works what we have calculated so far?
Compare the power of the source to the...
Exactly, very, very good idea. At the end, we should have energy conservation and power conservation should work for our circuit. So whatever the source outputs as power should be dissipated in our 4 resistors. So luckily, we have already calculated the total current. So we can calculate the total power from the source, or let's say the power from the source. The power from the source is the source voltage multiplied with this total current, which is the current I1. And this was 100 volts, this was 1 ampere, so we should get 100 watt. And we get. And this should coincide to the total power that is lost or that is dissipated in all the 4 resistors, which is just the sum of the 4, which is also 100, which nicely works. Okay. Then maybe let's get back to the LTspice simulation. And okay, I can also leave the circuit as it is here. So now we need to click on this button here for a new schematic. And the first thing that we need to, and maybe I will enlarge this just a tiny bit. The first thing that we need to have is the voltage source. And you can see there are lots of buttons here for a ground and for a resistor and capacitor and inductor and the diode, but there's no source. But there's another thing that is called component. So we can click on this component thing, and for you in the electrical, in the English bachelor program, it's way easier to use all these programs because they're all in English. It's a much more bigger hurdle for our German students. So voltage is a voltage source. So we use this voltage source and place it somewhere here. And then we need to have a resistor, and the resistor can be found over here. And they are automatically numbered. And I know from experience, even if it's not visible there, let me quickly press escape once again and make this window a bit smaller. And take a look at this lower left corner in a second. So I will use the resistor, and then in this lower left corner it says press Ctrl R to rotate and Ctrl E to mirror. And I know from experience that now the positive current through this resistor is pointing downwards. So if we want to have the resistor like over here pointing to, with some positive current pointing to the right, I need to rotate it once. Now the positive current would point to the left, upwards, and to the right. Unfortunately, the resistor always looks very similar, but don't ask me why it's like this in LTspice, but it is. And with another control R, now the current would once again point downwards. So here I will place R2, R3, R4. Okay, with space on the keyboard, you can always have a nice zoom, let's say, to fit the screen. And now we have the 4 resistors and the source. Now we can use the wire tool to wire everything together. And as you can see, if I'm wiring stuff together, these soldering pads will disappear. And at these points here, some junctions will appear. And maybe I will move this source a bit down and this also a bit down to have it more symmetrical. And maybe move this a bit to the left. Okay, this is looking quite nicely. My inner monk is satisfied. So what would be the next step?
Ground and pole.
Yeah, we need to have, I will omit the ground symbol for a second, but of course, if we want to simulate, we need to select what type of simulation we want to do, and we want to do the last thing here, which is a DC operating point. Yeah? We don't want to do transient analysis in time domain and no AC analysis with complex phases. We just want to calculate a DC operating point. Okay, and then it says, yeah, unfortunately, I don't know what the R means here. I need to have some values. So we need to give some values. And okay, it gives me also error messages for the other symbols and lots of error messages. So this is 30 ohm, this is 210 ohm, this is another 30, and this is 75, right? What we can see over there. And the source was 100. Okay, so now they all have values. If I simulate once again, then it says, unfortunately, you don't have a conducting path to ground. Please flag a node as a ground node. And this error message would not occur in the newer versions of LTspice. I think in this case, it's just ignoring it. So we will place a ground node here at the bottom. And yeah, and unfortunately, it's not visible in my recording because it's hidden behind my camera window. So I will make this window a little smaller. So there's the ground node. And now it's saying here, if you once again take a look at the lower left corner, this is ground. Why do we need this ground?
Reference node.
Exactly, because of this, what you talked in the lecture today, nodal voltage analysis. What happens in the background is nodal voltage analysis, and the very first step of nodal voltage analysis is select a reference node. And this is the reference node. This is the ground node, and all other nodes are automatically numbered. So this is node 1, this is node 2, this is node 3, because I have drawn the circuit in this way. And yeah, all what will happen in the background is that these nodal voltages will be calculated. So now we can simulate and we get some result. We see, okay, we get the voltages that we calculated before, something with 70 volts and 50 volts, and we get different currents, and we get the total current of 1 ampere flowing through our circuit. And in this result, you won't directly see the power because here you only see currents and voltages. But once again, take a look at the status bar. If I now hover the mouse over the resistors, we see, okay, there's a DC operating point with 1 ampere, 30 watts, 23 watts, 13.3 watts, 33.3 watts of power dissipation in this circuit. Yeah, so this is a nice way of solving such problems in a circuit simulator like LTspice. And this LTspice, what I can tell you, will also be available in the e-assessment center of our university.